So we continue our discussion on fiber optic sensors. So last time we had looked at the Mach-Zehnder interferometer sensor, right? So let's first quickly finish up that discussion. Right, so basically the setup was, so we take light from a source like a laser and then split it into two paths, fiber optic paths using a directional coupler, and then one of them is a sensing arm which detects, which is exposed to the environment, and then like its properties like the length of that arm or the refractive index is changed due to some external parameter, and then there's a reference arm which is fixed, and then due to the phase shift between these two, we have another directional coupler where we combine the paths, and then at the output we get a signal which is proportional to the phase shift, right, between these two, which is then proportional to the external parameter. So this phase shift, as we saw, could come due to a change in length or a change in the refractive index. Right. So, for example, if you use this as a pressure sensor, right? So the phase change per unit length of the fiber arm for a given change in some pressure delta P. Right, so from here you can write it like this. Right, so basically again, so the signal depends on change in the length due to the pressure and change in the refractive index due to the pressure. So if we take silica fibers, the usual silica fibers, then this quantity, which is gives me the change in length, is about 10 to the minus 11 radian per Pascal. Right, so the units of pressure are Pascal, as you know. So Pascal is Newton per meter square. Right, so if you take silica itself, like this quantity is about 10 to the minus 11. And then the change in refractive index is also about 10 to the minus 11 per Pascal. Well, not writing this. Right, so if you put these relative numbers, and then so again, let's say we are using a wavelength of 633 nanometer, then the phase change comes out to be about 4.5 times 10 to the minus 5 radian, right, per Pascal per meter of fiber. Right, and so we saw, like, from the taking into account the noise in the detector and also the source, the typical sensitivities are about 10. You can get 10 to the minus 6 or better sensitivity, right? So you can see here already. So for example, if you use 1 meter length of fiber, then 1 Pascal you can easily detect, right? If you use longer lengths of fiber, then you can detect lower pressures. So the sensitivity can be further enhanced, like if you coat the sensing arm with some material which responds, so where these quantities are larger. Right? So this is for bare silica. So you can coat the sensing arm with some other material which responds stronger to pressure. right? And you can typically boost this up by further order of magnitude. So typically you can reach like 10 to the minus 4 levels. Right, to get an idea of how sensitive this is, so the threshold of hearing, right, the lowest sound that human ear can detect. So as you know, sound waves are basically pressure waves, right? So the lowest sound that human ear can detect, right? So so the human ear is quite sensitive, right? So imagine like you're sitting in a very, very quiet room, and any small sound you'll be able to pick up, right? So that minimum sound that you can pick up corresponds to a pressure change of about 10 to the minus 5 Pascal, right? So it's a very small pressure change, you can see. So for example, if somebody is whispering, right, and you are at 1 meter distance away, that typically corresponds to 10 to the minus 4 Pascal. Okay, so you can imagine what levels of pressure we are talking about. Right, so if we take the arm length to be 100 meters, right? So with fibers, we can really make the length of the sensing and reference arms really long, right? We can just wind the fiber around some spool. So the device itself is compact, but we can get very long arm lengths, right? Which is difficult to do, for example, in free space interferometers. Right, so if we take length of 100 meter here, okay, and then let's take this pressure change at the lowest threshold of hearing, 10 to the minus 5 here, then this would imply the phase change at this level of sensitivity comes out to be about 10 to the minus 7 radian. Or 7 times 10 to the minus 7. Recall from the last class, we had sort of estimated from the noise in the detector that sort of the minimum measurable phase shift would be about 10 to the minus 8. So you can see this is above that, right? An order of magnitude above that. So you can easily detect like the minimum, the pressure change corresponding to just this minimum sound that human ear can pick up. Okay? So if we go to this level, then the minimum pressure change one can pick up is about 10 to the minus 6 Pascal. Right? So 10 to the minus 6 Newton per meter square. So that's a really, really small pressure change that can be detected. Okay, so this is for pressure. You could have other quantities, right? So basically, any other external quantity would also change typically this length and refractive index. So for example, instead of delta P, you could have delta T, but change in temperature, okay, or some other quantity. So for example, for a temperature sensor, this phase change per unit length of fiber per unit change in temperature, this is about 100 radian per Kelvin per meter. Right, so you can see this is a very large number here, right? So I can really pick up, so if, let's say the minimum phase change detectable is around 10 to the minus 7, or even 10 to the minus 6, you can see here that, right, so the temperature changes that you can pick up, right, are like 10 to the minus 10 or 10 to the minus 9. So you can pick up nano Kelvin change, 10 to the minus 9 changes in temperature, right? Very sensitive. Similarly, you could have like a force sensor, So this quantity is now about 10 to the 4 per radian per Newton per meter. Right, so now you can see again, so if I put the minimum detectable like 10 to the minus 8, then you can see we can pick up 10 to the minus 12. So 1 piconewton level of forces we can detect with like a meter of fiber length. So these sensors can be really, really sensitive. Okay, so yeah, that's all about the Mach-Zehnder interferometric sensor. So we discuss one more type of sensor, which is a rotation sensor, or also known as a fiber optic gyroscope. Right. So basically, for navigation systems, right? So for example, in airplanes or satellites, or basically where you want to know exactly where you're going, in which direction, and how you're oriented with respect to some inertial frame, right? So you need to measure like how much you're turning or how much you're rotating, right? So these gyroscopes are used in navigation systems. And so typically, like the earliest gyroscopes were just mechanical, right? So imagine a spinning top, like if you try to tilt it, the axis of the spin sort of tries to remain the same, right? It tries to sort of counteract the tipping. So these mechanical gyroscopes were the ones which were used, but they have limited sensitivity, and you can imagine like mechanical components are prone to wear and tear, right? So there's a question: relative phase changes are obtained from the intensities. Yeah. So recall, right? So after the second splitter, then we detect the powers in the detector, right? So for example, we saw that. So P1 went something like so. You have input power P0 from here, right? So this. So if you operate at the quadrature point, we saw this went something just like this, right? But this delta is now the phase change occurring due to the external factor in the sensing out, right? So just from measuring P1, we know P0 because that's just the input power, so we can calculate what. So yeah, we measure the power at the detector and then figure out what the phase change is, and then from the properties of the material, figure out what the change in the external parameter is. Right. So, but then we can make gyroscopes using again optical interference, right? Which can be much more sensitive, and also they are much more robust, right? There are no moving parts. We just have like some lengths of fiber and some light sources and detectors. So it's like one solid thing, no mechanical moving parts, and it can also be much more sensitive than the mechanical gyroscope. Okay, so nowadays mostly these optical gyroscopes are used. Okay, so this is based on the phenomenon of Sagnac interference. Okay, so this is just like the Mach-Zehnder interferometers. A Sagnac interferometer is also basically where you measure the phase difference between two paths taken by light, right? But so how it looks like, so you have some source which you couple into fiber. Okay. And then again, so because you have an interferometer, you need to split the light into two parts, right? So you have a directional coupler. Let's say a 3 dB directional coupler here. And so in the Mach center, we sort of had two parts, and then we recombined them using another directional coupler. But here what we do is basically sort of wound these two arms together so that one comes back to the other. Okay. So sort of we combine the output directional coupler also with the input directional coupler. There is only one directional coupler. Okay, so basically light comes from here, then it gets split into two here. Right. So now you can see in this sort of region where sort of we wound it around into loops multiple times. So you have one, so this part is traveling sort of clockwise in this loop, and this one is traveling anti-clockwise. Okay, so there you have two beams of light, one traveling clockwise, one traveling anti-clockwise. Okay, so again they sort of acquire some phase shifts here, and then they combine, they come back out here, and then recombine at this directional coupler, and then we take the other port. Okay, light coming out of the other port. One port is used for the input. Light coming out of the other port, we send it to a detector. Okay, and so if you just had this setup, then of course like the clockwise and the anti-clockwise are both traveling the same path, right? So there should be no relative phase shift. Okay, so in that case, what happens is, so the directional coupler, recall, it gives a relative pi/2 phase shift between the through port and the drop port, right? So if you look at the light coming into the detector here, right? So that consists of this anti-clockwise traveling light, right, which comes to the drop port here, right? And that anti-clockwise moving light came from the source again through the drop port, right? So this light consists of one part which is coming like this, going through and then coming back, right? So it crosses the directional coupler, so it goes to the drop port twice. Okay, so if we say that whenever you go to the other port, you get a pi/2 phase shift, like we discussed last time. Then basically, for this one, there will be a pi phase shift, whereas for the other one, that goes straight through here, then through this loop, and comes back again straight through here. So that is through port both times. So that path doesn't require. So because we're saying through port doesn't acquire any phase, the drop port acquires pi/2. So you can see that the two paths which combine to give me the output here will have a pi phase shift because one of them crosses this direction coupler twice. Right? So because we have a pi phase shift, right, and if this 3 dB, if we have equal powers, then basically they destructively interfere and you have no light at the detector. Okay, so if we have just this setup which is stationary, then basically these two paths cancel out and there is no light at the detector. Okay, so now imagine this whole setup is placed on some platform or like it's in some airplane or some satellite, right? And that's now moving. So if there is a rotation here, okay, so this is wound into n turns, right, off into some radius r, let's say, okay. So this loop encloses some area A. Okay, and then now imagine now this whole thing is rotating at some annual frequency omega. Then So when the light is entering here, right, then the light takes some time to go through these turns and then come back out. In that time, this thing has rotated a little bit, right? So when the light comes back out, you can see that one of the paths, so for this rotation, right, the light traveling in the same direction as the rotation, so the clockwise direction here, will have to travel a longer path because now this has moved a little bit here, so it will have to now go a little bit further till there, right, before it comes back out. Whereas for this anti-clockwise traveling light, it has to travel a smaller path because so it enters here, but then when it comes out, this has already moved here, so it moves less than what it would need to when it was stationary. Okay, so now you can see that the paths that the clockwise and anti-clockwise need to travel are now different because of the rotation. Okay, so that leads to a phase shift between the clockwise and the anti-clockwise, right? And because of that phase shift, now you'll get some light at the detector. So that is known as the Sagnac effect, right? This phase shift acquired due to rotation. So to understand what this phase shift would be, so let's imagine just a circular loop like this. Okay, so let's say that this point is where the light enters. This loop, okay. So again, so this has some radius r. Okay, so and let's say the direction of rotation is like that. Okay, so the light comes in here, then it splits into two. One clockwise, one anti-clockwise. Right, so now these paths are traveling, and let's say when they come back here, this has now moved. This input-output port has now moved here. Right, so this distance that it has traveled, let's say it's delta L. Okay, in some time delta T, which is which is the time taken by the light to traverse this path. Okay, so you can see that. Okay, so for what happens for the this clockwise traveling path, right? So the light traveling in this clockwise direction now has to. So it starts from here, and then has to come back all the way, not to the starting point, but a bit beyond that, right? Before it comes up. Whereas, if you look at the anti-clockwise path, so that starts from here, and then only goes till here, right? So it doesn't. It needs to travel a shorter distance than circumference. Okay. So let's consider the clockwise path, right? So this will be the clockwise path, right? Or let's first consider the anti-clockwise path, which will travel a longer distance. We need to travel a longer distance, right? So if we compute the time taken by the anti-clockwise traveling wave, Okay, so let's imagine this setup to be sort of the original Sagnac. This was so he first performed this experiment in 1930. So this is, let's imagine this light is traveling in free space. Let's not consider any medium for now. Okay, and that this path is perfectly circular. Okay, so this is a perfectly circular path of radius r, and the light is traveling in free space. Okay. So if we take, so what is the time that it took to go around this path, like starting from this input and then coming back out this output, right? So the distance traveled is, so again let's say this could have n turns, so the light travels n times around the circumference before coming out. Okay, so then the distance that it traveled right was n times the circumference, right? So that it went n times around, but then it had to travel this extra distance delta L, right, before it comes out, and then so to get the time, this is the distance divided by the speed c. Okay, and what is delta t or delta L? Sorry, delta L is basically the distance that this platform or spool traveled in time t1, right? So delta L is basically, so the velocity here is omega times r, right? That's the velocity times time. So that's delta L, right? So we can put this expression for delta L and then solve for t1. So you get t1 as okay. So that's the time taken by this anti-clockwise traveling wave. So now, if we look at the time taken by the clockwise traveling wave, so let's call that t2. So now it travels a distance smaller than this n times circumference, right? So again, like it comes here, enters the loop, and travels n times. But then when it comes out here, right? So it travels a distance delta L less than n times circumference, and then again divide by c gives me the time. And now again delta L I can write as omega r t2. Right, so from here we solve for t2 to get right. So of course you can see t2 is smaller than t1, right, because it had to travel a smaller distance. So the denominator here you can see is bigger than here. So t2 is smaller than t1, right? What we expect. So now the time taken by the two clockwise and anti-clockwise traveling waves is different. So when they recombine at the output, the phase shift that they acquire is different, right? So it's just one wavelength that we are sending in. So their frequency is the same, right? But when they recombine, the time that they have traveled is different, which means, so if you look at the time difference, so subtract these two. Right, we get that. So typically the rotation speed, so this is the speed at which the whole like platform or the where we place our detector, like that whole like airplane or satellite is moving, right? So the rotation speeds here typically will be much smaller than the speed of light, right? Because we're talking about mechanical movements. And actually, we would want to sense very small or slow rotations also for a sensitive detector. So basically this omega times r would be much smaller than speed of light. Right, so in this denominator we can just neglect this term. So delta t is basically that. Okay, and now so pi r square here is basically the area of the loop, right? So I can just write it as 4 times the area rotation rate times number of turns divided by. Okay. So now this difference in time will give me a phase shift between the two paths, right? Because again, phase, for example, so the temporal phase goes as omega times t. Right? So the difference in phase would be omega times delta t. Okay, so put omega in terms of lambda. So this phase shift comes out again to be proportional to the area, rotation rate, number of turns divided by the wavelength. Okay, so again the signal that we get at the detector here would be proportional to the phase shift. So you can see that the phase shifts, of course, proportional to the rotation rate that we want to measure, and the proportionality constant scales with the number of turns. So if you have more turns for the same rotation, we get a larger phase shift, and also the area enclosed by the loop. So if you have a bigger loop, which encloses a bigger area, then also we get a more sensitive detector. Okay. So again, this analysis was for the simple case of a perfectly circular path, right? And the beam actually traveling in free space. But what is remarkable is actually you could take any path. Okay. So what you could do is you could have a loop of any shape. Also, the medium could have any refractive index. Okay, so for example, this could be fiber or any medium that you want with some refractive index. Okay, so the area vector is perpendicular to the plane of this loop, right? And then you could have some rotation, let's say, right? So the rotation is also perpendicular to the plane of the angle. The direction of this angular velocity is also perpendicular to the plane of the rotation, right? So these two need not be the same, right? So where we placed our fiber loop or interferometer, so that's in some plane, and then you have some rotation in some other plane, right? So they need not be the same plane. So there could be some angle between a area vector and the rotation. So the angle between the plane of rotation and the plane where the light is traveling. Okay, and also there could be any. So this area enclosed is A, but the shape could be anything. Also, the medium in which the light is traveling could have any refractive index M. Okay, and you can do a similar analysis. Like we've done this very simple analysis that for free space and perfectly circular path. To do this kind of analysis, you need to actually do relativistic addition of velocities. Okay, so for a medium of refractive index n, you know that the speed of light in that medium is c over n, right? And now you have this rotation. So the medium itself is moving at some velocity, right? So that will be omega times, right? So this will be moving at some v, which will be omega times the position vector of this. Right? So basically the speed of light in this moving medium, you'll have to add the velocities, and because now one of the velocities is close to the speed of light, you have to use relativistic addition of velocities. You can't just do simple addition of velocities that we do in the non-relativistic case, right, where we just add the velocities. But for those of you who might have done some course on special relativity, for the relativistic addition of velocities, right, actually when you add the two vectors to velocity vectors, so the addition of two velocities, basically you have to do like that. So there is a factor in the denominator, which we typically neglect if u and v are much smaller than c. So we just say, okay, the addition of the velocities is just do this. Okay, but so here, for example, u would be c over n, right? So then you can't neglect with respect to c. So you have to use relativistic addition of velocities, and not only that, there is also length contraction, right? So this is moving now. So the length, again, for those of you who might have done special relativity, so if you have some length L which is moving, right? So to us who are in the stationary frame, this length actually appears shorter. So this length actually appears shorter by factor which is known as given from the lower velocities, and you have to take this length contraction to compute this phase shift. So we won't go into the details of that, but what is remarkable is that from that calculation, so for any arbitrarily shaped loop and light traveling in any medium of index n, the phase shift that you get is actually this exact same formula. Okay. So this formula works for any arbitrary shaped loop for any light traveling in any medium. So actually the medium refractive index doesn't show up at all in the phase shift. The phase shift just depends on the rotation. Actually, so for the general case, when they're not in the same plane, you have to take the dot product of the area and the angular velocity vector. Right, so basically you take the projection of the angular velocity vector onto the, so basically the rotation in the plane of the interferometer is what will give you, will contribute to the phase shift. Right? So this general formula holds for any general loop, right, and for any general medium. So it works for our fiber loop also, of course, right. Okay, so right, so we can use this formula for the phase shift for our fiber optic gyroscope. So for example, consider a fiber optic gyroscope where this bound the fiber into a spool of radius 5 centimeter. Let's say we have 1500 turns of the fiber around this. Okay, so this gives me a total fiber length so 2 pi r times n. So that comes out to be about 470 meters. So again, we can get really long path lengths in a small compact form factor using fibers, right? So that's an advantage. So let's say again we use a wavelength of 850 nanometer. So from this formula, the phase shift comes out to be about 1.16 times the rotation rate. Okay, so let's say we place this on the surface or on the ground. So now we know that the Earth is rotating, right? So the rotation rate of the Earth, right? So it completes one rotation 360 degrees in 24 hours. So the rotation rate is 15 degrees per hour. Right, so So if you convert this to radian per second and then put it in here, that corresponds to a phase change of about 10 to the minus 4 radian. So 8 times 10 to the minus 5. Okay, so for example, if you want to sense the rotation of the Earth, that's the level of phase shift you need to detect, right? And again, the way we are detecting the phase shift is again how much power comes out of this port of the directional coupler, right? So the sensitivity would be again given by the noise in the detector here itself. So it will be similar to the sensitivity in terms of phase shift would be similar to the Mach-Length interferometer, right? So from that you can see that we should be able to detect this level of phase shifts easily. So as we discussed, so if you have zero rotation, then basically the two paths destructively interfere and there should be no light at the detector, right? But now when you have some rotation, there is some phase shift and there is some light at the detector. So if we call this light at the detector PD, so then PD we can write as, so this is P naught. We put power here. So P naught. So it will be given by the same formula, sine squared delta phi by 2. Right? So you can do the same analysis here. So this path will have a phase shift, this path will have a phase shift. So now there will be a phase difference between these two paths coming back together here. And then we want to see what power comes out of the output port. So same thing as the Mach-Length interferometer. So the power in this port will go as sine square of the phase difference between the two paths. So you can see if delta phi is 0, then PD is 0. Right, so again we can try for linear operation, we can operate at the quadrature point, right? So have a fixed phase difference pi by 2, and then this extra phase shift will be due to the rotation, the external rotation, right? So this fixed pi by 2 phase shift, for example, can be done if you have like a phase modulator, for example, you insert a phase modulator in one of the in the path, right? And basically, if you use a traveling wave phase modulator, so this has some electrical input here. So some V of t, which gives me a phase shift. Proportional to the voltage that I apply, right? So if you have a traveling wave phase modulator, basically what happens is, so you apply a electrical signal, so that's like an electromagnetic wave traveling at a very low frequency, like a microwave frequency or RF frequency, right? The electrical signal, and then you have the optical wave traveling through this phase modulator. So for the traveling wave modulator, basically this phase shift will happen only when both of these are traveling together. Okay, if they're traveling opposite to each other, then the phase shift does not happen because of basically you don't have phase matching. Okay. So this will give a phase shift only on one of the, so let's say only on the clockwise. Right, so if you apply the right voltage, we can have a difference, we can have a phase pi by 2. Okay, so only on one of the directions it applies a phase. So we can have this fixed pi by 2 phase difference between the two parts. So the question is, why is the refractive index not showing up in the final formula? So that's the question. As I said, basically what you have to do to derive this in general is to use this relativistic addition of velocities and then this length contraction. So turns out that when you do that, in the final formula, basically the n does not show up. Okay, so what determines this phase shift finally is basically this length contraction that is happening, and the relativistic velocities between the two paths, right? And basically that difference turns out does not depend on the absolute velocity of the light. Okay. So this is actually a very remarkable result, right? And it's very surprising that actually the medium does not matter and does not show up in the final formula. So, but yeah, the only way you can say is that basically, so what is finally happening is this phase shift is a relativistic effect, okay, and it's not coming from the absolute sort of phase shifts acquired by the light in the medium. It's actually coming from this relativistic effects, which does not depend on the absolute properties of the light, like the speed of light in the medium. Okay. So it just only the rotation rate is so on how the frame is changing, right? So the relativistic effect is how the frame is changing. It's basically how this thing is rotating. Only that shows up here. So yeah, I mean, it's very surprising, but that's how that. So if you naively just calculate without taking relativity into account, if you just naively try to calculate, okay, this is the path and time taken by the light in this direction and this direction, then you will get a incorrect formula, right? So there probably you'll end up with some formula with refractive index n. But as I said, in this case you cannot ignore relativity because the absolute speed of light is of course close to speed of light in free space. So you have to use relativistic addition of velocities and also length contraction. So it turns out basically, yeah, the final phase shift is decided by these relativistic effects of the frame of reference and not the absolute properties of the light in the medium. So but yeah, so that's why this formula is kind of remarkable, right? Even for rotation velocities which are very small, right? So this rotation or omega times r, as we saw, would be much less than c, right? So in that respect, like none of the things are moving here anywhere close to speed of light, but because the light in this medium is moving close to the speed of light in free space, relativity comes into the picture, right? And then the final formula is decided by the relativistic effect, even though this thing is not moving anywhere close to the speed of light. So this is one sort of surprising case where, yeah, relativity, you can see the effects of special relativity without anything moving close to the speed of light. But yeah, so this is the exact formula for any loop of any shape and loop being placed at any angle with the rotation. Okay, so again, yeah, if you operate at the quadrature point, then you can do this Taylor expansion and then get this linear relationship between the phase shift and the power detected. And again, if we assume the detector to be short noise limited, then we can calculate a minimum detectable phase shift, which is basically the same formula that we had for the Mach Zehnder interferometer, right? So this rho is the responsivity of the detector. Right, this is the electronic charge, and delta F is the bandwidth. So that's inverse of the averaging time. Okay, and then so from this relationship between the phase shift and the rotation here, this translates to a minimum detectable rotation rate. Okay, so again, if I want a very sensitive gyroscope which can detect very small rotations, then again I need more turns, loop of a bigger area, higher input power, higher laser power helps, and higher averaging time or lower bandwidth helps. So yeah, so to sense the rotation of the Earth, right? So this kind of phase shift, the rotation of the Earth gives like a 10 to the minus 4 level phase shift. So we can see how that compares to the minimum detectable rotation rate here. So again, so let's assume 5 centimeter loop. Total fiber length, let's assume so this 2 pi r times n. Let's assume that to be 1 kilometer. Okay. So I think n comes out to be like 3000 something. And then, so again, take typical numbers for the responsivity, 0.5 amp per watt. Let's use optical power 1 milliwatt. Again, wavelength 850. Average time 1 second. So this is 1 hertz, delta F. So then this omega minimum comes out to be about 10 to the minus 8 radian per second. Okay, so if we convert this to again, so remember the Earth's rotation rate is 15 degree per hour. So if we convert this to degree per hour, so this comes out to be about 0.003 degrees per hour. Right, so you can see that these gyroscopes can be sensitive to rotations which are like 4 orders of magnitude lower than the Earth's rotation rate. Okay, so again, they can be really, really sensitive to small changes in direction.